Hello and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about the diode connected MOSFET. And essentially today we want to analyze the small signal of the diode connected MOSFET and solve for what's called the AV gain, where the AV gain is minus Gm Rout, and the equation of the AV gain minus Gm Rout was proven in a video called Cascode Amplifier Small Signal Analysis Part 1, which I did in the past and is posted in the top right hand side corner of this video. Before we dive into the analysis, we want to know two things. And the first thing is that this RD here is essentially used to set the DC bias current, which is denoted as ID. And also we need to note that the drain terminal is connected to the gate terminal for a diode connected MOSFET, and here is my source terminal. The second thing we want to note is the importance of a diode connected MOSFET, and there are a couple main important reasons why we want to consider a diode connected MOSFET. And the first is that it acts as the perfect precision resistor, where a polysilicon based resistor has a big base, right? It's huge. And if we wanted to embed this into our microchips, we will not have a lot of real estate to work with. So the diode connected MOSFET allows us to have a small signal resistance, which is approximately 1 over Gm in the fraction of the space when compared to this physical resistance up here. The second thing we can use the diode connected MOSFET is to copy over currents and do what is called the current mirror. And the main reason we are doing the diode connected MOSFET is because in the next video, I will be talking about the current mirror, and we need to understand the diode connected MOSFET in order to understand the current mirror configuration. The third important thing about a diode connected MOSFET, and again, these three things are not the only thing that are important about it, but just something we want to kind of study or point out, is that the diode connected MOSFET allows us to have a stable active load. And essentially what that means is we will find out that the AV gain of the diode connected MOSFET is dependent on its GM, or its transconductance. And essentially the GM equation is this 2 mu n COX omega over LID, where we could manipulate the active load to only be a variable dependent on the width and the length of my MOSFET. As a result, it is independent of temperature. So if temperature changes, our gain will remain the same. And if the manufacturing drifts in any way, our gain will still remain the same. Again, these three examples are meant to give a base as to why we're studying this diode connected MOSFET. I hope that makes sense. Please leave any questions or concerns you may have in the comment sections below, and I'll be sure to get back to you. Okay, so let's go ahead and find the AV gain of this diode connected MOSFET, where AV is equated to minus Gm Rout. And what I'll do is I'll break this into two parts. The first part being solving for Rout, and the second part being solving for Gm. So we know from past videos that Rout is equated to Vout over Iout, where Vin in this situation is equated to Vout, again because they are at the same node. So in order to solve for Rout, what I'm going to do is I'm going to label this an Iout. I'm going to label the current that it splits here as In. I'm going to label the current that flows in here as I capital D. And I'm going to label the current that goes here as IO1, and the one that goes in here as IO2. So I hope that makes sense. And what we can obviously say is that In is equated to 0 because there's an open circuit here. So no current can flow through that. Let me call this equation number 1. We can write an equation for ID and call this Vout over RD, right? Because the voltage drop across RD is V out. So the current is going to be V out over RD, and we can call this equation number 2. We can write an equation for IO1, and this is essentially just V out over RO, which we can call equation number 3. And lastly, I want to write an equation for VGS. And again, VGS is VG minus VS. And we said that VG is the same voltage as the voltage at VD. So this is going to be VD minus VS. And we know that VD is equals to V out. And VS is simply 0 because it's connected to ground. So then this just becomes V out. So VGS is equated to V out, and I'm going to call this equation number 4. Okay, so now let's write an equation for I out. And what we're going to do is we're going to use KCL. So we're just going to solve for current. We're going to say then that I out is equated to IO1 plus IO2 plus ID plus IN. And we know that IN here is 0. So we can say then that I out is equated to IO1 is going to be equation number 3. So it's V out over R out. IO2, so plus IO2 is just this voltage controlled current source. So it's going to be GM. VGS we take from equation number 4. It's just V out plus ID is the current through RD, or equation number 2. So we can say then that ID is going to be V out over RD. So then now we can say then that I out is equated to V out over 1 over RO plus GM plus 1 over RD. So then R out, which is equated to V out over I out, is equated to 1 over RO plus GM plus 1 over RD. So therefore, we can say then that R out is equated to RO in parallel with 1 over GM in parallel with RD. So I hope this makes sense. Again, if you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. So now there are 2 things we want to note about our results. And the first thing is that consider RO is much greater than RD, which is much greater than 1 over GM. Where again, RO kind of ranges from 20K all the way to 100K ohms. RD, on the other hand, ranges from 5K to about 10K ohms. And this entire 1 over GM can range from 1 milli to 10 milliohms. As a result, R out will be approximated to 1 over GM, because if you take a very small resistance and put it in parallel with bigger resistance, you get simply approximated the smallest resistor. Something that should be noted is that this case is what we also considered ignoring channel length modulation. So what's called gamma is equated to 0, or RO is equals to 1 over 0, which is approximately infinity or a very large resistance. As a result, R out is essentially just 1 over GM. The second thing we want to note is that in our equation, R out, which is equals to RO in parallel with 1 over GM in parallel with RD. In the case of no RD, so instead of using RD to set my DC bias current, I have a current source as my ID. The output resistance of the diode connected side is simply only these two. All right. So in general, the R out is only going to be RO in parallel with 1 over GM for a diode connected MOSFET. where my current is just provided by a current source. And as a result, this can also be approximated to just 1 over Gm if we ignore channel length modulation. So again, I hope this slide makes sense. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. So now the second part of this analysis is finding the transconductance Gm. So then we can say then that Gm is equated to I out over V in, where V out is simply equals to V in because they are the same node. And if we note that this is going to equate to I out, and since V in is the same as V out, this is just I out over V out, which again is just 1 over R out. So then this means that Gm is equated to 1 over RO plus Gm plus 1 over RD, where if we consider that RO again is much larger than RD, much larger than Gm, this here goes to 0, and this also here goes to 0. So then Gm is simply equated to my Gm, or my transconductance, located right here. So the final conclusion for the analysis of this diode-connected MOSFET is that the AV gain is equals to minus capital Gm R out, which is simply equals to minus Gm times 1 over Gm. And this is an approximation, which is equals to minus 1 V over V. So this ends the analysis. If you have any questions or concerns, please leave them down in the comment section below, and I'll be sure to get back to you. If you liked the video, please give it a thumbs up, and please share the video to your colleagues and friends so they can also obtain the knowledge given in the video. And if you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.